recreate a simple game of hide and seek, which I'm sure you're all familiar with. Now, this premise may seem simple, but we believe that this combination between GPS and robotics will have a major role in the future, and we will show you how through this demonstration. But first, a bit about how our GPS system works. Our GPS system operates using 24 satellites. These satellites can send signals down to the Earth. The atomic clocks built onto these satellites will measure the time it takes for these signals to reach Earth and back to within a nanosecond. And using this time, it can calculate distance. In order for these satellites to measure location in all three dimensions, that is longitude, latitude, and altitude, accurately, you need at least 4 satellites. An important part of GPS history to our project was when President Clinton turned off selective availability in the year 2000. Before it was turned off, the military had been scrambling GPS signals, so for the civilians, GPS was only accurate to within about 100 meters. But presently, GPS technology has an error margin of about 1 meter or up to 5 meters. For our GPS in particular, it was 3 meters. And this precision was very important for us because our project is on such a small scale.
Over the course of this project, we had to use various types of equipment. The first one and the most important one was the NXT brick. The brick is the so-called brains of the robot. With this brick, we took the program code, which was written in Robot C, which is a language similar to C, but it has some specialized robotics functions, such as motor and sensor capabilities. So the program code would be downloaded onto the brick, and the brick would translate it into instructions for the robot to use. Attached to this brick, we had various types of sensors. The first being a touch sensor, which simply tells the robot whether or not the button is being pressed, a compass, an ultrasonic sensor that we use to help the robot detect and avoid obstacles, and a GPS.
So in order for this project to work, we knew we really need some kind of wireless communication between the two robots. And originally we were going to use Bluetooth. It has a short range and it's relatively slow, but it has low power, and more importantly for us, it was built into the brick itself. Unfortunately, as we'll explain later in the presentation, we did run into some problems with Bluetooth. So we ended up having to switch to NextBeats. NextBeats are a longer range than regular Bluetooth. They run on the XBeat wireless communication protocol. Unfortunately, they do need a third-party component. You need to buy 2 of them.
As for our actual project, we divided our project into 3 phases. Before reaching full autonomy in phase 3, we go through semi-autonomy in phase 1, which involves a stationary target and a human-controlled robot. Phase 2, which involves a stationary target and a robot that can move itself. In phase 1, we had 2 pieces of equipment: a controller, a handheld controller, and a seeker robot. The purpose of phase 1 was to make sure that the robot could perform all the calculations necessary. Don't have to worry about motor functions. The GPS sensor, which is connected to the controller, will send data about the current location to the seeker robot, which already identified for the destination. With this information, the seeker robot could calculate the angle at which it needed to move, and consequently the direction it needed to turn left or right. It would then display on the screen left or right, and us, with the controller, we have to turn it left or right using a combination of 3 buttons. At this moment, is there anyone in the audience that would like to come and test out the movement capabilities on our phase 1 robot? Go ahead.
The state table in the upper corner, which Richard is currently explaining to our volunteer, shows the different combinations of buttons you would need to press down in order to navigate the robot. The 1 denotes that the button is being pressed down, the 0 denotes that it's not. So for example, to go forward, you need to press down both the left and the right sensor, while to go backward, you only press the middle.
Some of you may be wondering how exactly this robot can triangulate its position. As I said earlier, it has data about the current location and the particular destination. As denoted by preferable y degrees. The red arrow is the direction the robot is currently facing, which is arbitrarily x degrees. The robot knows this because of the compass sensor. By comparing x degrees in the blue and y degrees in the purple, the computer robot can find out which one's left or right. For example, if x degrees is larger than y degrees, as it is on the diagram, the robot will try to turn right, and otherwise it will turn left, so that the red arrow lines up with the long side of the triangle.
Very much.
I was trying to get it to go to you, but it wasn't working.
Alright, so the next phase of our project was to have the robot drive itself with autonomous. In this case, we're going to simulate this by Wally, and he wants to get to the flower in order to do this, we have to move all of the code that we had on the controller to the robot. So we already had code that knew what distance we had to turn and what we had to travel. But we had to move that from the controller to the robot. In addition, we also had to write some new code that would let the robot turn itself. At the moment, in phase 1, the robot will rely on the operator to do that. In phase 2, there is one. And at this point, the target is still stationary. It doesn't jump away. And this is where we were going to have a video demonstration. We were going to film it last night. It rained last night, and the robots did not like the rain. So instead, we have a little slideshow thingy to explain it. So the first step is you have to pair the controller with the GPS using the process of connecting something to the control pairing. You do that on the target, and you do it on the robot with different GPS. And then you start both programs on the robot, and these robots, those programs then communicate via the next speed that we talked about earlier, and the target will then send its GPS coordinates over to the robot. The robot then uses that information to calculate its path from where it is currently to the target, and make purpose self-driving. Alright, so the next phase of our project was having an autonomous robot that moved toward the moving target. In this case, it's Eve. This is significantly more difficult than moving to a stationary target. If Wally, he has cameras, assuming cameras, and he can just track where he is with his eyes, but our robot doesn't have cameras and can't do that. So we have to constantly hold the target for its position, and this turned out to be more than we could accomplish in the time frame of the promise.
Over the course of this project, we ran into a couple challenges. The first one was with the overall communication between the controller and the target and the mobile robot. In our original design for this project, we were going to use Bluetooth to have the handheld controller communicate with both the GPS and the mobile robot. However, we soon discovered that when a GPS receiver is involved, the NXT bricks Bluetooth has to be placed into what is called raw mode, which means that only one Bluetooth channel can be opened. Therefore, we had to find a different way to communicate between the mobile robot and the handheld controller, which we found to be the next phase, which Ryan talked about earlier. The other problem that we had, Ryan also alluded to earlier, was a lack of testing opportunities for the robot. Since this project relies so heavily on GPS technology, we have to test the robot outdoors. Because GPS technology does not work indoors, it does not work if there are any tall buildings or tall trees around. So we had to go to a wide open field where there was nothing else around to interfere with the signals. In addition, it had to be a nice day out because, as Ryan said before, robots don't like rain or wet. So this severely limited the number of times we were able to successfully test the robot. The whole purpose of this project was so that we could discover the ways that autonomous robotics and GPS devices could be combined for future real-life uses. One use that we think that this could be potentially used for would be in unmanned aircrafts. These aircrafts, since they would not require a pilot, would be able to go into more dangerous environments. They'd be able to be used to fight wildfires and to fly directly into a storm system. They'd be able to collect new data for scientists to use so that they could better understand these environments. In addition, these robots can be used instead of humans to explore toxic environments, such as places where there's been a chemical spill or in a nuclear site. The use of robotics would make it so that people do not have to be exposed to those dangers.
This combination between GPS technology and robotics can also be implemented in the military, for example, during search and rescue missions. When a field has been compromised by fire or falling infrastructure, it is more effective and more efficient to send a robot which can navigate itself through the field using GPS to look for wounded or dead soldiers instead of risking more lives to look for these casualties. In addition, another way in which robots may be useful is situations where a bomb may be involved. Insurgents typically will trigger these bombs if they see another human or a vehicle approach the location where the bombs are set. Robots are generally more compact and harder to see, so therefore you run less of a risk of having the mission fail. And even if the bomb does go off while the robot is trying to remove or defuse it, at least you're not risking a
At this moment, we would like to thank a few people that we found out to complete our project without. First and foremost, we would like to thank Ashley So, our project advisor, who offered us a lot of support and kept us on track the whole way. We'd also like to thank Miss Elizabeth Mabry and our technical assistant, Nico Shaw. They're actually from the very beginning, making sure we understood the nitty-gritty details of autonomous robotics, GPS system, and code. We would also like to thank Mr. John Antoine and Ms. Ali Rosen and the Government School Board of Overseers for offering us this wonderful opportunity to work. We would also like to thank all our sponsors. Last but not least, we're grateful to our parents for allowing us to attend this program. That's it. Are there any questions?